What's up, fam? Back at it again. May 5th, day 34, I believe, 5 p.m. Said we were gonna do this today. Because it's just applying Dijkstra's algorithm. And I've already done it yesterday once on LeetCode. So this is supposed to be a piece of cake. Um, yeah, this is supposed to be a piece of cake. So what I want to do first is to create the adjacency list and then actually calculate the shortest path. And then fill in the unreachable nodes. And then I'll return shortest here, right? So first I want to create the list. After I do this question, I'm going to work on the prep. Check out the haircut. Yeah, okay, so adjacency list. You want to first create an unordered map. The key will be the node, right? And then the pair, the value would be a pair of destination and weight, right? And then for All right. And then for every vector in times time and times, what you want to do is I'm talking to my vlog.
Vlog? I'm talking about vlogs?
Yeah. Fuck.
Oh my God.
What you want to do is adjacency list and then time 0, which is the source, right? Will be equals to the pair, which is time 1 and time 2, right? Which is the node and then the weight. Oh no. Oh no, man.
This is not true.
Nah, it's fine.
Leo xịtตัวอะไรxịtอ่ะ
Mong sige.
Ủa xịtตัวLeo xịt chú cái
Bảo bảo này, xúc, xúc, mẹ.
bà mua xịt chú bà dùng cái xịt ăn chơi
Cos'è xúc xúc?
cái gì đó
Sit down. I think that'll work, right? Yeah, so that will populate the adjacency list. I believe so. Oh, no, 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 it's wrong. It's wrong. Yeah. Like that. No, this is actually right. Okay. No, right? Shortest will be of what type?
Like this, the chin, lift the shoulders as high as you can. The leading text of consciously roll the shoulders back. Generous. So you read the rest of this practice.
Right? Destination and account.
Straight.
No, this could be destination time, I believe. Is where it gets confusing. And then the container. I don't know, right? Yep. On this right. And this would be time and node. Because you want to sort according to time, right? Mhm. And then you want to first push priority. No. Then he push. What you want to push is pair of 0 and K. Won't matter. So you want to go wow. min heap is not empty. Right? What we want to do is current. Minimum. Pop it. If shortest not defined. This is the part where I don't really remember. So you first want to confirm that min heap is not empty. Let me look at it. There like that. Wait one. So
Bring your belly towards your body. Shift weight to the left, one step back. And I'll to the left, so like I know. Exhale, straight, front leg, in from your hips, start reaching.
meaning pulse. And now you want to do a BFS. Neighbor and adjacency list.
Shift the weight back to the heels. Then hinging from your hips, arms will reach forward as the belly is resting on the right side. Shift the weight into the right side. And reach your arms up high, lunge.
How to iterate through this list for
Down. Rebend the front knee, shift your weight forward, lift the back leg for warrior three. Option to rest on fingertips on the mat and support. And then make a lifted legs, slowly standing up, put the knee into your chest. Stack towards the place to your gaze. Inhale. Press, it's left leg back, stacking against the lunge. The lunge on the sector. And other.
Or
Keeps spreading your chest. And exhale the breath out, look down for balance. Head and shift your forwards. Shift the weight to the front foot as you lift the back leg. Stacking left side hip over right. Focus your gaze on one spot.
I guess for this, the one is the node, right? Mhm. Yes. Right, I think that's right. Um, you can find it. I just find it. Right. I have to return the max of the map. Oh, why is it not working? Why is the Wi-Fi not working, my friend? So I just iterate through it.
States. And your game on one spot.
Something like that. I don't really know when to use the arrow or when to use this. Force. 報到呢個，我點我報到呢個，我報到呢個，
唔係啊，你前排咩本身嚇？你呢排都戴緊呢個？唔係光年眼鏡咩？
佢嗰個係 JBBNT 眼鏡噶嘛？
我睇
哦，我明啦。
哇！又大咗，哇！好恐怖啊！你見到佢開得快到癲咁樣平均。你望住呢幾個花，你等陣做嘢做到等等，即係你可能做多陣，睇下呢個開咩？喂，超快！
咁熱
或者或者你而家記住呢個花有幾大，記住佢有幾大，
哦，
等等佢應該就開到佢咁大。點解佢成咁？
嗯哼。Right, because they're one indexed. Is there something wrong? Oh, what the fuck? Am I stupid? Typo. Typo. Typo alert. Typo alert.
Why am I being shushy? Why am I being shushy?
So
Look, Ligo's really not it. Ligo, Ligo's not. It's not. 佢朋友好少少，佢朋友 at least you know looks 17, 18,
I
but
think a regular ABG.
right, but 佢 just not it. 要提一提醒佢 just not it. 即係 you can go for 呢個 look, but it's not look.
I don't know, man. I mean, a friend is kind of cute though.
The friend looks her age.
你唔好笑佢啦。
想 but I think it's not it.
其實我喺度笑佢，好 fucked up。
There's nothing wrong with dressing like this, you know, but it's not it. That's the problem. 即係你着完好似個 friend 咁，fine 咯。Sorry.
Ah! Right? I got it, but I want to like I want to draw it out so that I actually understand it, right? I want to look up Dijkstra's. This guy's a genius, by the way.
Today, I'm going to teach you how to run Dijkstra's algorithm on a weighted directed graph. Dijkstra's algorithm tells you the shortest distance from one node to every other node in the graph. This differs from prims and crusticles, which result in minimum spanning trees. Let's use the following graph for our example. We'll keep a list of unvisited nodes at the bottom. Our first step is to pick the starting node. Let's choose A. We'll use the table on the right to keep track of distances. Remember, the distances we are measuring are from our starting node, A. We put 0 for A and infinity for the others, as we haven't visited them yet. The next step is to examine the edges leaving A. We can reach B and C from A, so let's update the chart with the corresponding costs. Next, we look at the chart and pick the smallest edge of which the vertex hasn't been chosen. In this case, C. Let's cross off C in the unvisited node list, marking it as closed. After choosing C, we examine the edges leaving C and update the chart accordingly. B is now reachable from A with the cost of 3 by traveling through C. Also, D and E become reachable for the first time. Let's do the same thing as before, choosing the smallest path with an unclosed node. This time it's B.
I want to like paint it out for me. I want to see how the min heap incorporates the, you know, right. Okay. Yeah, this is what I need.
Hi there, welcome or welcome back to my channel. If you have always wanted to understand and delve into the depths of Dijkstra's algorithm, then
Mhm.
this is the video for you.
Hit me.
Here is a weighted graph where each one of the nodes represents a town. The number that is associated with each edge between towns is the cost or the distance in miles between them. If our source node is C and the destination is E, what is the shortest path between these two nodes? In other words, what is the path with minimum cost between these two nodes? Now, there are multiple paths to node E, right? So, for instance, this could be one path. The cost of this path is 2 plus 4 plus 6 equal to 12. Here is another path, and the cost of this path is 5 plus 8 plus 3 equal to 16. And this is another path here whose cost is 2 plus 5 plus 3 equal to 10. So if you manually do the calculation, you'll see the minimum travel cost is 10. And how do we arrive to that answer programmatically? So this is the kind of problem that can be solved using Dijkstra's. That's why it's used a lot in GPS devices to find the shortest route from the current location to the destination. Dijkstra's algorithm finds the shortest distance between two nodes on a weighted graph. Conceptually, it is quite similar to a breadth-first search algorithm, although the key distinction is that breadth-first search works on an unweighted graph or a uniform cost graph. So for example, let's say the cost to travel between all nodes is 1. We could run a breadth-first search to find a shortest path in this case. I would highly recommend that you check out my video on breadth-first search if you'd like a refresher. During the traversal, we'll keep track of the distance cost to reach a particular node from the source node in a dictionary. We don't know anything right now, so we'll set their values to infinity or the maximum value possible. Once we discover their costs during the traversal, we'll set the values appropriately.
So instead of doing this, you make like a vector, right, of all the, okay, yeah.
We'll be using
You initialize a vector of size n, and then you make a vector of size n. You make a vector of pairs of size n. And then the first element of the vector would be the node. Right? And then the second element would be the shortest path. And then you would initialize it with all like infinity, which is max int. Okay.
a
Int
min
max.
heap data structure for the execution of Dijkstra's algorithm. Okay, so let's step through the algorithm. The gray color of the nodes indicate that they are undiscovered.
Okay, lads, I'm going to pause the recording for now because I really want to take a big doo-doo. So give me a sec. And we back at it. Let's see.
Once we have navigated to it and are in the process of examining all the connections originating from the node, we'll consider that node discovered and change the color to orange. After completing the examination and navigating away from the node, we will mark it as explored and modify the color to green. In this algorithm, every time we process a node, we need to do two things. The first is to update the distance cost estimates of the connected nodes in the distances dictionary if it's less than its current value. The second is to choose which node to navigate to next. The node to navigate to next will always be the one with the minimum cost from the source node.
Right.
We'll use a min heap to make that determination, and you'll see how we do that in a second.
Okay.
Our source node is node C, and since we are starting from it, its cost is 0. We'll update that information in the distances dictionary. Since we are exploring node C, we'll change its color to orange and heap push a tuple containing node C.
Right. Okay. So that would be the step, right? Mm-hmm.
And its cost to the min heap. This way, our min heap will always have the node with the minimum cost at the top. So this is where we'll start our while loop.
Yep.
While there are elements in the heap, we will heap pop the first element. Node C is connected to 3 nodes, heap pop the first element. Node C is connected to 3 nodes, A, B.
We'll heap pop. It will heap pop. Right? So this is popped. And I have, wait, one. Where's the shortest distance? So it will always pop the shortest distance.
E and D. The distance between C and A is 2 miles, and the current cost to reach C is 0. Therefore, the total cost to reach A is 2 plus 0, which equals 2. Since 2 is less than A's cost in the dictionary, we'll update the estimate to 2 and push it on to the min heap. Note that the color of node A is changed to orange to indicate that it is discovered. The distance between C and B is 9 miles, and the current cost to reach C is 0. Therefore, the total cost to reach B will be 9 plus 0 equal to 9.
Mm-hmm.
Since 9 is less than B's cost in the dictionary, we'll update it to 9 and push node B and its cost to the heap.
So this loop that she's talking about right now would be this, right? So first I push shortest, which is the source. Right? And this only happens if it's the first one, right? It's the first ever time, because if it's the second or whatever time, then I'll see it, right? So first ever time, I will, boom, I have shortest now. So this is indicating that it's orange. And then I will do, so this only happens for the source node. And I'll look at the neighbors. And if I don't see the neighbor in shortest, then I'll push it. Then I'll push it. Where's the current estimate? And then I will go to the top, which is the minimum distance, which is the next minimum, which is A in this case, right? So now I'm at A. And then I'll pop it. Yeah.
Separate out.
Shortest. If I've already seen it, it means that there is already another shortest path. Right? Because if I've not seen it, if I've seen it before, it means that that node has been through this, which doesn't make any sense. Which means that from the source node, there is another path that they've already gone there, right? So, so I've never seen it. Then I'll set it. So A right now has a weight of 2 in shortest. And then I'll go for all the neighbors. So A to F to B to C, right? Let's say I could go to C. But C already have a distance, which is 0. Let's say it does, right? Shortest dot find. So, but C I can find, right? So I wouldn't push it because it means I already have a shorter distance. So now I have to B and to F. To B and to F. Right? B there is. D there is in the heap. I see. Okay, and then yeah, and then it's done, right? And then I push. So basically I push B and F into it. And then top would be to C. It wouldn't be pushed, right? So the top would be to B somehow, somewhere to B. The distance would be 2 plus 5, right? Yep. Okay. Yeah, I get it. I get it. I get it. I get it. And then you'll want to fill in the unreachable nodes. Like if you can't find the shortest I, like shortest I is not present, means that it cannot be solved, right? And if you do this,
And mark it as discovered. The distance between C and D is 5 miles, and the current cost to reach C is 0. The total cost to reach D is 5 plus 0 equal to 5. Since 5 is less than D's cost in the dictionary, we'll update it to 5 and heap push D and its cost onto the heap, marking it as discovered. Since we have finished exploring all connected neighbors of node C, we'll mark C as explored. As node A has the minimum cost, it is the topmost element in the min heap, so we'll heap pop it to process it next. The elements in the min heap data structure are not necessarily sorted, but anytime you heap push or heap pop, it will maintain the heap property of keeping the element with the minimum value at the top. In our case, the tuple containing the minimum distance will be the topmost or the first element. Please do check out the linked video in the description for a deep dive into the heap data structure. Dijkstra's algorithm is a slight modification from the breadth-first search algorithm. In breadth-first search, you also explore all the neighbors of a node, but then you randomly pick any one of the neighbors. In this case, we pick the nearest neighbor. That is the only difference between the two. Let's examine the distance estimates of the unexplored nodes connected to node A. The distance from node A to node F is 4 miles, and the current cost of A is 2 miles. So the total cost to travel to node F is 4 plus 2 equal to 6 miles. 6 is less than the current value of F in the distances dictionary, which is infinity. So we update F's cost to 6 and also heap push it onto the min heap and mark it as discovered. The next node connected to node A is node B, which is located 5 miles away. The current minimum cost to node A is 2 miles, hence the total cost to B is 5 plus 2 equals to 7. Since 7 is less than the current value of node B's cost in the dictionary, we will update the cost to 7. We will also heap push B and its spots of 7 to the min heap. With all connected nodes of node A examined, we'll mark it as explored. Now notice that there is already a value of B with a cost of 9 in the heap. This is acceptable because the cost is from a different route. From this current route, which is via node A, the cost is 7. Since 7 is less than 9, it will take a higher priority over 9. Now, node D is the topmost element in the heap, and so we'll heap hop and process it next. Node D is connected to node B. The distance between D and B is 8 miles. The current cost of node D is 5 miles, so the total distance to node B is 8 plus 5 equal to 13 miles. Since 13 is greater than B's current cost of 7 miles, we will leave it as it is. With all neighbors of node D examined, we will mark it as explored. The next element with minimum cost is node F, and so we'll heap hop and process it next. The only unexplored node connected to node F is E, which is 6 miles away. Therefore, the total distance to E is 6 plus the current cost of F in the distances dictionary, which is also 6. So 6 plus 6 equal to 12 miles. Since 12 miles is less than E's current value of infinity, we will update the value to 12. That node E, which is 3 miles away. The total distance to node E is the current cost of B, which is 7 plus 3 equal to 10. Since 10 is less than E's current value of 12, we'll update E's cost to 10. We'll heap push node E and its cost of 10 to the mid-heap. We can now mark node B as explored. The next element in the min-heap is node B with a cost of 9. However, since we have just finished exploring B, we'll simply heap up this element from the heap and take no further action. We've reached the last stop node E with a cost of 10. Let's first heap up it from the heap. Since it has no unexplored neighbors, there is nothing left to process, so we can mark it as explored. Let's then heap up the next element, which is also node E. Since we just finished exploring it, we'll do nothing. Oh, adjacency left, which represent the nodes in.
Yeah, I get it. I fully get it now. Okay. Yep. I guess I can do it again tomorrow. And solidify in my brain. Yeah, it's a lot of syntactic stuff. And the first and second for the adjacency list is different from the min heap, some little details like that. But yeah, I feel like today we did pretty good. The Dijkstra's and yeah. So prims would be to create a minimum spanning tree, but Dijkstra's is to find the shortest path, right? Minimum spanning tree is how to connect nodes with the minimum number of edges such that every node is connected, right? I think that is the definition of minimum spanning tree. Right? Or it's to visit all node with minimum cost, right? Yep. Without any cycles and with the minimum possible total edge weight. Yep. And the spanning tree whose sum of edges weight. So there should be n minus 1 edges, right? Because for every additional vertex or node that you add, there should be 1 extra edge. So you would loop it until there are n minus 1 edges. Yep. I think that's correct. So what is after Dijkstra's is my question. Minimum spanning trees, shortest path. Greedy. No greedy algorithms. I fucking love Eli 5. Eli 5 Reddit is so good. Anyways. I see. That's what it means. I didn't know. Okay, so greedy is like you're looking only at short-term approach, right? You want to get rich quick and you only make the best decision for you now. So it's kind of like dopamine, right? You blow your money now instead of saving it for later for an even better outcome, right? It's like Togi. Instead of saving all the money that he's he's like getting now and buying a house, putting in S&P 500 and getting Nvidia, instead he gambles it even more, right? For the chance of making even more money. Okay, yeah, makes sense. Makes sense. Often greedy algorithms only generate approximations to optimal solutions because you don't consider the long-term advantage, or you don't make a more exhaustive breadth first decision. Okay, right. I think it makes sense. Right. This is the key of Dijkstra's, right? All weights in a graph must be non-negative. Yeah, because if you add non-negative and negative weights, like it can fuck up the, yeah. Mhm. Mhm. So what is traveling salesman problem? We will leave that for tomorrow because right now I am going to practice my interview for Wednesday. I'm gonna shave, do this, call it a day. See you tomorrow. Oh, this one. So I did this one today. Beautiful stuff. This one I did myself. My own solution. Dijkstra's plus min heat. It has to be. It just has to be. Okay. All right. Peace and love. Work hard. JBNT. Come on.